Picture the most violent explosion in the universe, a collision so cataclysmic it sends ripples through the fabric of space itself. Two neutron stars, each more massive than our Sun, but crushed into a sphere no wider than a city, slammed together at nearly the speed of light. In less than a heartbeat, they unleash more energy than a billion suns, forging elements so rare and precious they would shape the destiny of planets yet to be born. And here's the staggering truth: your very existence, the gold in your jewelry, even the device you're using right now, might owe their existence to this apocalyptic cosmic dance. This isn't science fiction. It's the spine-chilling reality of how our universe operates. Neutron star collisions are nature's ultimate alchemists, transforming the raw stuff of dying stars into the heavy elements that make life possible. Every speck of gold on Earth, every shimmering vein of platinum, even the uranium that powers our cities, they weren't born in the quiet fires of our solar system. They were forged in the heart of a stellar catastrophe so violent it defies comprehension. And the wildest part, these explosions might hold the key to unraveling one of the greatest mysteries of our cosmos. Where did Earth's treasure trove of precious metals truly come from? We're about to embark on a journey back in time, to an era before planets, before the sun, even before light itself had a clear path through the newborn universe. We'll follow the trail of cosmic shrapnel flung across galaxies, piecing together how these unimaginable collisions crafted the very atoms that built our world. Along the way, you'll discover how scientists turned detective, using ripples in spacetime and flickers of gamma rays to trace gold's extraterrestrial origins. This isn't just a story about stars, it's the story of you, of everything you've ever touched, and the celestial violence that made it all possible. So buckle up. The universe is about to reveal one of its most dazzling secrets. To understand the cosmic alchemy behind Earth's gold, we first have to witness the brutal birth of neutron stars, the universe's ultimate pressure cookers. These celestial oddities don't form gently. They're born from chaos, the smoldering corpses of massive stars that dared to live too large. Picture a star 20 times heavier than our Sun, burning furiously for millions of years, fusing lighter elements into heavier ones until its core resembles an onion with layers of carbon, oxygen, and iron. But when it reaches iron, the party stops. Unlike other elements, fusing iron doesn't release energy, it steals it, like a cosmic thief robbing the star of its final fuel reserves. And then, catastrophe. The star's core collapses in less than a second, triggering a supernova explosion so bright it outshines entire galaxies. What's left behind isn't just a corpse, it's a zombie. The core's gravity is so intense that protons and electrons fuse into neutrons, packing a sun's worth of mass into a sphere no wider than Manhattan. This is a neutron star, where the laws of physics twist into knots. A single teaspoon of its material would weigh billions of tons on Earth. Its surface gravity is so strong that if you dropped a marshmallow from just 1 meter up, it would hit the ground with the energy of an atomic bomb. But the real magic happens when two of these ultra-dense monsters spiral toward each other, locked in a death spiral by gravity's unrelenting pull. Their collision unleashes a firestorm of creation, flinging neutron-rich debris into space at nearly light speed. In this shrapnel, something extraordinary happens. Free neutrons latch onto atomic nuclei, building heavier and heavier elements in a process called rapid neutron capture, or the R process. It's here, in the wake of this apocalyptic embrace, that gold, platinum, and other cosmic treasures are forged not in the slow burn of stars, but in the violent aftershocks of their demise. This means the ring on your finger or the circuitry in your phone might be made of stardust, but not just any stardust. It's the ashes of a cataclysm so rare, astronomers estimate it happens only once every 100,000 years in a galaxy like ours. Every precious metal on Earth was likely born in the heart of a dying star's last, desperate act, a final gift to the cosmos, scattered across space to one day become part of planets, oceans, and even you. In the vast cosmic arena, few events rival the sheer spectacle of two neutron stars colliding. Think of it like this: the universe has countless stars, but only a tiny fraction meet the exact conditions needed for this kind of cataclysm. First, both stars must be massive enough to collapse into neutron stars in the first place, which already narrows the field. Then, they need to be born as a binary pair, locked in a gravitational dance that lasts billions of years without drifting apart or getting disrupted by other celestial bodies. And finally, their orbits must decay over eons until they spiral inward, culminating in a collision so violent it briefly outshines every star in their home galaxy combined. The numbers behind these mergers are mind-bending. When two neutron stars finally collide, they release more energy in a few seconds than our Sun will produce in its entire 10 billion-year lifetime. The explosion generates gravitational waves, ripples in spacetime, so powerful they can be detected across the universe, along with a blinding flash of gamma rays and a fiery afterglow visible across multiple wavelengths. But here's what makes these events truly special: they're vanishingly rare. In a galaxy the size of the Milky Way, astronomers estimate a neutron star collision happens only once every 100,000 years. That means since modern humans first walked the Earth, our galaxy has witnessed fewer than 2,000 of these cosmic fireworks shows. What makes these collisions even more extraordinary is how precise the conditions have to be for heavy elements like gold to form. The outer layers of the merging stars get shredded into a swirling, superheated disk, while the cores themselves might collapse into a black hole in milliseconds. In that brief window, however, the escaping material becomes a nuclear laboratory unlike anything on Earth. Neutrons flood the debris at unimaginable densities, slamming into atomic nuclei and building heavier elements through the R process, nature's version of a high-speed assembly line for precious metals. Without this exact chain of events, the right masses, the right timing, the right explosion, the periodic table would look very different, and Earth's treasure trove of gold might never have existed. Yet despite their rarity, we've been lucky enough to catch one of these events in action. In 2017, gravitational wave detectors picked up the telltale chirp of colliding neutron stars, followed by telescopes spotting the resulting Kilonova explosion 130 million light-years away. That single observation confirmed what theorists had long suspected. These mergers are cosmic gold factories. The explosion produced an entire Earth's worth of gold in seconds, along with other heavy elements flung into space at a fraction of light speed. It's humbling to realize that the gold in your jewelry might trace its lineage to a similar cataclysm, an explosion so distant and ancient. It happened before dinosaurs roamed our planet. So when you hold something made of gold, you're not just holding metal. You're holding stardust forged in one of the universe's most extreme environments, a relic of a violent and beautiful process that connects you to the cosmos in the most intimate way possible. These collisions are more than just spectacular light, shows they're the universe's way of recycling itself, turning the ashes of dead stars into the building blocks of new worlds. And somehow, against all odds, those building blocks ended up here, in our solar system, in our planet, and in our hands. The moment that changed astrophysics forever came on August 17, 2017. Date scientists now refer to simply by its discovery code, GW170817. For the first time in history, humanity didn't just hear the universe's secrets through gravitational waves or see them through telescopes. We experienced both at once, like suddenly gaining a new sense. It began when the LIGO and Virgo gravitational wave detectors picked up a ripple in spacetime unlike anything they'd seen before. The signal lasted 100 seconds, far longer than the black hole mergers they'd detected before, and its frequency spiraled upward like a cosmic siren. But this wasn't just a chirp, it was a scream. Within seconds, coordinates flooded astronomers' inboxes, and telescopes around the world swung into action. Less than 2 hours later, the SWOPE telescope in Chile spotted something extraordinary, a pinprick of blue light in galaxy NGC 4993, 130 million light-years away. Unlike a supernova's slow fade, this flare vanished in days, replaced by a glow that shifted to red as heavy elements like gold and platinum cooled in its aftermath. The event checked every box for a neutron-star merger. The gravitational waves matched theoretical predictions, the light curve fit Kilonova models, and spectroscopy revealed the unmistakable fingerprints of the R process at work. This wasn't just a discovery, it was a revolution. Before GW170817, neutron-star collisions existed only in equations and simulations. Now we had proof they were real and that they forged the universe's heaviest elements right before our eyes. The data revealed staggering numbers. The merger ejected up to 5% of the sun's mass in pure gold and platinum, along with other R process elements. To put that in perspective, the debris from this single event contained enough gold to gild every planet in the Milky Way 1,000 times over. But the real breakthrough was the power of multi-messenger astronomy. Gravitational waves told us how the stars moved, while light revealed what they created, like piecing together a crime scene with both security footage and DNA evidence. For centuries, astronomy relied on light alone. Now, we're listening to the universe's vibrations too, and the combination is unlocking mysteries even Einstein couldn't have imagined. GW170817 proved that when neutron stars collide, they don't just shake spacetime. They seed galaxies with the ingredients for planets, life, and even the devices you're using to watch this right now. Every precious metal in your home is a love letter from the cosmos, written in the ashes of a cataclysm we've only just begun to understand. The aftermath of a neutron-star collision isn't just an explosion, it's a cosmic foundry operating at temperatures hotter than the sun's core. When these ultra-dense objects finally merge, they don't just vanish quietly, they go out with a bang so spectacular it redefines the word violence. The resulting Kilonova explosion is like nothing else in the universe, a fireball that forges elements at breakneck speed while flinging them across interstellar space at nearly 1/3 the speed of light. For perspective, imagine taking every nuclear weapon ever built and detonating them simultaneously. That wouldn't even come close to matching a single second of this celestial detonation. The initial collision releases so much energy, it briefly outshines every star in its host galaxy combined. But what happens next is even more astonishing. As the neutron star's outer layers tear apart, they form a swirling disk of superheated debris around the newborn black hole or hypermassive neutron star at the center. This disk becomes the universe's most extreme chemistry set, where temperatures exceed 100 billion degrees and pressures crush atoms into entirely new forms. Within this maelstrom, something miraculous occurs. The extreme conditions trigger rapid neutron capture, the R process where atomic nuclei gorge on free neutrons like starved travelers at a cosmic buffet. Normally, adding neutrons to an atom makes it unstable, but here, the density is so overwhelming that nuclei can't decay fast enough before more neutrons pile on. This process builds atoms heavier than iron element by element, climbing the periodic table at incredible speed. In mere seconds, a single neutron star collision can produce more gold than exists in entire star systems, along with platinum, uranium, and other heavy elements that would take normal stars billions of years to create through ordinary fusion. What makes Kilonova truly special is their telltale glow. Unlike supernova, which fade over weeks, these explosions change color dramatically in days, starting with an intense blue as freshly minted radioactive elements decay, then shifting to red as heavier metals like gold cool and dominate the light spectrum. This color evolution is our smoking gun, proof that the R process is happening in real time. When astronomers spotted this exact sequence during GW 170817, it confirmed what theorists had suspected for decades. These explosions are the universe's primary factories for heavy elements. The numbers involved are staggering. A typical kilonova can eject up to 5,000 Earth masses worth of pure gold and 10 times that in other precious metals. To visualize that, picture a sphere of gold larger than Mount Everest, vaporized and scattered across light years of space. Over billions of years, these elemental ashes mix with interstellar gas, eventually becoming part of new stars and planets. Our solar system likely formed from a molecular cloud enriched by multiple neutron star collisions, meaning the gold in your jewelry isn't just stardust, it's the literal fallout from one of the universe's most catastrophic events. Perhaps most mind-bending is the time scale. The gold atoms created in these explosions spend eons drifting through the void before being incorporated into planets. Some might land in an asteroid, only to be delivered to Earth via meteorite impacts billions of years later. Others could end up in the core of a distant exoplanet, forever locked away from sight. The gold we mine today represents just a fraction of what arrived on our planet. Most sank to Earth's core during its molten youth, meaning we're only scratching the surface of a treasure trove deposited by ancient cosmic cataclysms. This revelation transforms how we see the periodic table. Elements like gold aren't just there, they're refugees from the most extreme events in existence, survivors of a journey that began with stars dying in spectacular fashion. Every time you hold something made of platinum or gold, you're touching material forged in conditions so extreme, they make the sun's core seem tame. The universe doesn't just create these elements, it blasts them into existence in explosions so rare and powerful, they shape the chemical makeup of entire galaxies. And somehow, against all odds, those atoms found their way to you. The cosmic recipe for gold isn't just about extreme heat and pressure. It requires a secret ingredient so rare it only exists in nature's most violent moments. That ingredient is rapid neutron capture, or the R process, a nuclear chain reaction so fast it makes ordinary star chemistry look glacial. While most elements form slowly in stellar cores over millions of years, the heaviest metals like gold and platinum require a different kind of kitchen, one where neutrons bombard atomic nuclei at breakneck speed before they have time to decay. Think of it like two chefs cooking with the same ingredients but different methods. Regular stars use the slow process, or S process, where atoms leisurely absorb neutrons one by one over centuries, climbing the periodic table like a patient gardener tending vines. This produces about half the elements heavier than iron, things like barium and lead, but stops far short of gold's atomic weight. The S process is like baking bread at low heat, predictable, steady, but incapable of reaching the temperatures needed for more complex dishes. Now imagine throwing that same dough into a blast furnace. The R process in neutron star mergers works at speeds the S process can't touch. Neutrons flood atomic nuclei faster than they can stabilize, creating ultra-heavy isotopes that rapidly decay into stable precious metals. In less time than it takes to snap your fingers, a single atom can gulp down dozens of neutrons, ballooning in mass until it fractures into multiple heavy elements. This isn't just fast, it's nuclear alchemy at relativistic speeds, where a teaspoon of neutron-rich debris can transform into a treasure chest of rare metals before cooling into cosmic dust. The key difference lies in the neutron supply. In ordinary stars, neutrons trickle in slowly from side reactions, limiting how quickly elements grow. But during a neutron-star collision, the violence shreds atomic nuclei apart, releasing a tsunami of free neutrons at densities exceeding 1,000,000 tons per cubic centimeter. It's the difference between filling a glass from a dripping faucet versus standing under a waterfall. These extreme conditions allow the R process to forge elements all the way up the periodic table to uranium, and beyond elements the S process could never dream of creating. What makes the R process truly remarkable is how precisely it solves one of the universe's great mysteries. For decades, astronomers puzzled over why gold exists at all in our solar system. Ordinary stars can't make it, and supernova, once thought to be the primary heavy element factories, prove surprisingly bad at it when modeled. But neutron star mergers provide the perfect crucible, with their neutron-rich debris and absurd energies. Computer simulations now show that a single merger can produce enough gold to seed an entire galactic neighborhood, explaining why trace amounts appear even in ancient meteorites. Yet the story doesn't end there. Recent discoveries suggest the R process might have a dark twin equally violent, but even more elusive. Some hypernova explosions and magnetar births exhibit the right conditions for rapid neutron capture, hinting that multiple cosmic catastrophes might contribute to the universe's heavy metal supply. This revelation turns the periodic table into a forensic record, where every gold atom carries clues about the violent event that birthed it. Whether forged in colliding neutron stars or born in the death throes of supermassive stellar magnets, these elements are more than just chemicals, they're cosmic archaeology, telling the story of how the universe turns stardust into treasure. Gold doesn't just appear in the universe, it's forged under conditions so extreme they defy everything we know about chemistry. While supernovae are spectacular, they're actually terrible at making gold. The reason lies in the delicate balance of neutrons and protons needed to build heavy elements. When a massive star explodes, its core collapses into either a neutron star or a black hole, but the outer layers get blasted outward in a shockwave. That material is hot, yes, but it's also expanding too rapidly for atomic nuclei to capture enough neutrons to climb the periodic table all the way to gold. Supernova can cook up lighter heavy elements like zinc or copper, but gold, that requires a neutron buffet, and only one cosmic event serves that up reliably: the collision of two neutron stars. Here's what makes these mergers so special. As two neutron stars spiral together, their crushing gravity peels away their outer layers, creating a swirling cloud of ultra-dense matter. This debris isn't just hot, it's saturated with free neutrons, packed so tightly that atomic nuclei can't help but absorb them. Imagine trying to walk through a blizzard without getting hit by snowflakes. That's what it's like for atoms in this environment. Each nucleus gets pummeled by neutrons, bulking up instantaneously into unstable, overweight versions of themselves before decaying into stable heavy metals like gold and platinum. This happens in seconds, a blink compared to the millennia required for slower stellar processes. The smoking gun for gold's origin lies in the numbers. When astronomers calculated how much gold exists in the Milky Way, they found that supernovae could account for less than 1% of it, but neutron-star mergers. A single collision ejects up to 500 times Earth's mass in pure gold. Multiply that by the estimated merger rate over the galaxy's lifetime, and suddenly the math makes perfect sense. There's another clue in meteorites, ancient space rocks that contain traces of heavy elements in proportions that match our process predictions perfectly. These cosmic time capsules prove that gold was already floating in the cloud that formed our solar system, a relic of mergers that happened billions of years before Earth existed. So why doesn't all this gold end up swallowed by black holes? The secret is in the ejection speed. When neutron stars collide, some debris gets flung outward so fast, over half the speed of light, that it escapes the newborn black hole's gravity. This material becomes interstellar treasure, drifting for eons until it's swept up in new star-forming regions. Our solar system likely formed from a nebula peppered with gold-rich dust from multiple mergers, explaining why even Earth's crust holds more gold than supernova alone could provide. And here's the wildest part, we're still collecting this cosmic inheritance today. Every time a gold-bearing meteorite lands on Earth, it's delivering material forged in a neutron star collision that predates our planet. This revelation reshapes how we view our place in the cosmos. The gold in your jewelry isn't just beautiful, it's a time capsule from an event more violent than anything humanity could imagine. It survived billions of years in space, witnessed Earth's formation, and outlasted countless civilizations before reaching you. Every precious metal we cherish is, in essence, stardust twice over, first forged in the hearts of dying stars, then refined in the apocalyptic collisions of their remnants. The universe doesn't create gold casually. It demands catastrophe, rarity, and the perfect storm of physics to mint these cosmic coins, and somehow, against all odds, they ended up here in our hands. Platinum isn't just another shiny metal, it's a cosmic detective story written in the aftermath of neutron star collisions. While gold often steals the spotlight, platinum and its rare metal cousins tell an equally dramatic tale of celestial violence. These elements don't form in the gentle fusion reactions of ordinary stars. Like gold, they require the neutron-rich chaos of merging neutron stars, where a single teaspoon of debris contains enough rare material to fill a bank vault. Take platinum's atomic structure, it's heavier than gold, with 78 protons compared to gold's 79, which means it needs even more extreme conditions to form. During a neutron star collision, the R process doesn't discriminate. It builds entire families of heavy elements simultaneously. The same neutron-rich environment that forges gold also produces platinum, iridium, and osmium in staggering quantities. In fact, the Kilonova observed in 2017 ejected enough platinum to coat every planet in our solar system several times over. these metals emerge together like a cosmic set of triplets, born from the same unimaginable pressures. Uranium tells an even wilder story. The heaviest naturally occurring element on Earth shares the same extraterrestrial origin as your wedding ring. Unlike lighter, radioactive elements that form in supernova, uranium's 92 protons require the neutron bombardment only a kilonova can provide. Recent simulations show that a single neutron star merger can produce uranium atoms with such violence. They're flung across galaxies like subatomic shrapnel. Some of these uranium fragments eventually found their way into Earth's crust, where we now mine them for nuclear fuel, meaning the energy powering our cities comes from the same cosmic explosions that crafted our jewelry. Rare earth metals add another layer to this interstellar saga. Elements like neodymium and europium, critical for smartphones and electric vehicles, were long thought to form mainly in supernova. But new research reveals neutron star mergers may be their dominant cosmic source. The key lies in the lanthanide rush, a sudden surge of neutron capturing reactions that occurs in kilonova debris. This process creates not just familiar precious metals, but entire groups of exotic elements that modern technology depends on. Your phone's vibrator, your headphone's magnets, even the screen you're watching this on, all contain atoms forged in the same explosions that made Earth's gold. What makes these elements truly special is their scarcity across the universe. The Milky Way contains 100 times more iron than all these R-process elements combined, a testament to how rarely the perfect conditions for their creation arise. Unlike carbon or oxygen that sprinkle generously through space, platinum and uranium are cosmic loners, formed only in the most violent and precise of stellar deaths. Their presence on Earth isn't just lucky, it's evidence that our solar system formed from a molecular cloud unusually rich in the ashes of ancient neutron star collisions. The eerie precision of these events becomes clear when you examine metal ratios. Meteorites and ancient stars show nearly identical proportions of platinum to gold to uranium, a fingerprint matching our process predictions perfectly. This consistency across billions of years suggests neutron star mergers haven't changed their recipe since the universe was young. Whether in the oldest stars or in your catalytic converter, these metals maintain their cosmic ratios like a secret code from the universe's most extreme alchemists. Perhaps most remarkably, these elements become time capsules when they reach planets. Earth's surface platinum is relatively scarce because most sank to the core during our planet's molten youth. The deposits we mine today likely arrived later via meteorite impacts, meaning your platinum jewelry might contain atoms delivered by asteroids billions of years after Earth formed. This two-stage delivery system, first from the collision that created the elements, then from the space rocks that transported them, makes every rare metal a twice-told tale of cosmic violence and celestial wanderlust. These metals do more than just fill periodic table gaps, they connect human technology to the universe's most awe-inspiring events. The platinum in your car's catalytic converter once swirled in a superheated maelstrom around a newborn black hole. The uranium powering nuclear reactors spent eons drifting through space before Earth existed. Even the europium making your smartphone screen glow red can trace its lineage back to a flash of light so powerful, it briefly outshone its entire galaxy. Every time humanity unlocks a new use for these elements, we're having a conversation with the universe, one that began when two dead stars collided in the dark. The newly minted gold and platinum from a neutron star collision don't just sit around waiting to be discovered, they embark on an epic voyage across the cosmos. Picture this: within seconds of the merger, the explosion hurls heavy elements outward at astonishing speeds, some exceeding 30% the speed of light. This isn't a gentle sprinkling of stardust, it's a cosmic shotgun blast, spraying precious metals across light years of interstellar space. These elemental fragments don't travel alone. They hitch rides on shockwaves from the explosion, mixing with interstellar gas like cream swirling in coffee. But what happens next is even more extraordinary. This metal-rich debris becomes part of the galaxy's recycling program, waiting to be incorporated into new generations of stars and planets. For millions of years, these golden shards drift through the void, enduring extremes that would obliterate anything crafted by human hands. They withstand the crushing radiation of pulsars, pass through the gravitational maelstroms of black holes, and survive supernova shockwaves that reshape entire star systems. Along the way, they mix with other interstellar material, hydrogen gas, microscopic dust grains, and remnants of dead stars, slowly accumulating into vast molecular clouds. These cosmic nurseries, cold and dark, become the raw material for new solar systems. When such a cloud collapses under its own gravity, the precious metals from ancient neutron star collisions get woven into the fabric of future planets like cosmic glitter mixed into celestial dough. Our own solar system likely formed from one such enriched cloud some 4.6 billion years ago. Chemical analysis of meteorites, the oldest unchanged rocks in our solar system, reveals an astonishing truth. They contain tiny grains of gold and platinum isotopes that could only have formed in the process of a neutron star merger. These metallic time capsules prove that long before the sun ignited, before planets took shape, our corner of the universe had already been seeded with heavy elements from stellar catastrophes. The distribution tells a fascinating story. While most of these precious metals sank to Earth's core during our planet's molten youth, later asteroid impacts delivered fresh supplies to the surface. That means the gold in your jewelry might come from two distinct cosmic deliveries. Some atoms arrived during Earth's formation, while others were delivered later by gold-rich meteorites. This interstellar delivery system works with surprising efficiency. Computer simulations show that a single neutron star collision can enrich thousands of future star systems within 100 light years. The metals don't spread evenly, they form concentrated veins within molecular clouds, like rivers of gold flowing through space. When these dense pockets collapse to form stars and planets, they create worlds with unusually high concentrations of precious metals. Earth might owe its rich gold deposits to being born in one such cosmic sweet spot, a stellar neighborhood particularly wealthy in neutron star debris. Other planetary systems could be far poorer in these elements, making our metallic abundance a rare cosmic gift. The journey from collision to civilization spans almost unimaginable timescales. Consider that most of Earth's surface gold arrived via meteorites during the late, heavy bombardment around 4 billion years ago, meaning those atoms spent over half the current age of the universe wandering space before finding a home. Some might have cycled through multiple generations of stars before ending up in our solar system, each stellar lifetime purifying and concentrating the metals further. This recycling explains why gold is so chemically pure in nature. Cosmic processes have been filtering out impurities for eons before humans ever mined it. Perhaps most remarkably, we're still receiving deliveries from this cosmic supply chain today. Every year, Earth accumulates about 30,000 kilograms of extraterrestrial material, much of it containing traces of heavy elements from ancient stellar explosions. While most arrives as microscopic dust, larger gold-bearing meteorites still occasionally streak through our atmosphere, the final leg of a journey that began with colliding stars. This ongoing exchange means the gold in your pocket might contain atoms that reached Earth relatively recently in cosmic terms, perhaps only a few million years ago, making them late arrivals to a planetary treasury that's been accumulating for billions of years. This celestial distribution system has profound implications for life itself. Heavy elements like gold and platinum aren't just pretty, they are essential for modern technology, from electronics to medical devices. More fundamentally, the uranium that heats Earth's core and drives plate tectonics, a process crucial for maintaining our planet's habitability, comes from these same cosmic explosions. Without neutron star collisions scattering their metallic bounty across the galaxy, Earth might have been a geologically dead world, incapable of supporting complex life. Every time you hold something made of these precious metals, you're touching the final link in a chain of cosmic events that made our world possible, a story of destruction and creation written in atomic ink across the canvas of space and time. Meteorites are more than just space rocks, they're time capsules carrying secrets from the dawn of our solar system. Among their most startling revelations are tiny grains of heavy metals with isotopic fingerprints so distinctive, they could only have formed in the cosmic crucible of neutron star collisions. These metallic anomalies tell a story written in atomic code, revealing how Earth became enriched with gold, platinum, and other precious elements billions of years before humans walked its surface. Take the famous Allende meteorite that fell over Mexico in 1969. Inside this charred remnant of the early solar system, scientists found microscopic inclusions of metals with neutron-rich isotopes that defy ordinary stellar origins. The key clue: their atomic signatures matched theoretical predictions for rapid neutron capture the R process, with precision no supernovae could replicate. Like finding a distinctive manufacturer's stamp on a piece of jewelry, these isotopic ratios point directly to neutron-star mergers as their birthplace. The meteorite's platinum isotopes, for instance, show an overabundance of forms like platinum-198, an atomic configuration that requires the neutron flood only a kilonova can provide. Even more compelling are certain ultra-rare meteorites called CB chondrites, which contain metal droplets that froze within hours of our solar system's formation. These droplets hold the highest concentrations of R process elements ever measured in extraterrestrial material, some with iridium levels 10,000 times richer than Earth's crust. Their chemical composition forms a perfect bridge between computer simulations of neutron star collisions and the actual heavy metals we find on Earth. It's as if these space rocks captured a direct sample of the universe's most exclusive alchemy, frozen in time before planets even formed. The timing of this cosmic inheritance is equally remarkable. By analyzing radioactive isotopes like iodine-129 in meteorites, researchers can trace when these heavy elements arrived in our solar system's building blocks. The evidence suggests most were injected into our molecular cloud between 10 and 100 million years before the Sun ignited, a blink in cosmic terms. This narrow window aligns perfectly with the estimated rate of neutron star mergers in our galaxy, implying our solar system might owe its metallic wealth to just one or two nearby collisions during this critical period. But meteorites reveal another twist. Not all heavy elements arrived at once. Some grains show isotopic ratios so extreme they must have formed in separate merger events tens of millions of years apart before becoming mixed together in our solar nebula. This layered timeline suggests Earth's gold didn't come from a single cosmic cataclysm, but from multiple stellar explosions that each contributed their unique metallic signature. Like different vintages in a fine wine blend, these varied origins give our plan, its heavy elements, a complex pedigree spanning generations of stellar deaths. Perhaps most astonishing is what these space rocks tell us about gold's journey to Earth. While meteorites confirm neutron star collisions as gold's birthplace, they also show our planet received far more of this precious metal than the average solar system object. The Moon's crust, for example, contains about 1/200th the gold concentration of Earth's accessible layers. This discrepancy hints at a late-stage delivery system. After Earth formed, a final bombardment of gold-rich meteorites may have showered our planet with extra metallic wealth. Some theories suggest this final delivery came from the shattered remains of a protoplanet that once orbited between Mars and Jupiter, its metal-rich core scattered across the inner solar system in a cosmic game of billiards. These meteoritic clues do more than satisfy scientific curiosity. They rewrite our understanding of the universe's chemical evolution. Before these discoveries, astronomers assumed supernova were the primary source of all heavy elements. Now, meteorites prove nature has a far more exotic recipe for creating cosmic treasure, one that requires the perfect storm of colliding dead stars and astrophysical luck. Every gold atom in your jewelry carries this incredible history, forged in a stellar apocalypse, scattered across light years, and finally delivered to Earth via celestial messengers that outlasted the dinosaurs. The next time you hold a piece of meteorite or a gold coin, remember, you're touching the physical evidence of one of the universe's rarest and most violent events, preserved across billions of years by the patient hands of cosmic time. Supernova were once considered the universe's ultimate element factories, colossal explosions capable of forging every heavy metal in existence. But when scientists tallied up the cosmic inventory, they hit a mystery. These stellar explosions couldn't account for all the gold, platinum, and uranium in the galaxy. The problem lies in the physics of the explosion itself. While supernovae create lighter, heavy elements like iron and nickel with ease, their environments lack the neutron density needed to build truly massive atoms efficiently. Imagine trying to fill a bucket with a garden hose versus a fire hydrant. Supernova are the hose, while neutron star mergers are the hydrant. The critical difference comes down to timing and neutron availability. In a supernova, the core collapse happens so rapidly that most neutrons get locked into the newborn neutron star, leaving the ejected material relatively neutron poor. Elements like zinc or copper form readily, but the ladder to gold requires grabbing dozens of neutrons in milliseconds, a feat only possible where free neutrons outnumber protons by 100 to 1. Neutron star collisions create this perfect storm, shredding the ultra-dense stellar remnants into a neutron soup where atoms bulk up faster than they can decay. Supernova, by contrast, spread their energy over too large a volume, like a chef trying to sear a steak by waving it through a candle flame. Spectroscopic analysis of ancient stars reveals the smoking gun. These cosmic fossils, formed before neutron star collisions had time to enrich the galaxy, show strange elemental patterns, plenty of strontium and barium supernova products, but barely detectable gold or platinum. Later generation stars display the opposite, R-process elements in abundance. The transition aligns perfectly with models showing neutron star mergers take hundreds of millions of years to become frequent enough to seed the galaxy. Supernova dominated the early universe's chemistry, but it took colliding neutron stars to mint its most precious coins. Computer simulations expose another flaw in the supernova theory. Even when programmed with ideal conditions, supernova models struggle to produce more than a few Earth masses of gold per explosion, far short of the Milky Way's observed abundance. Neutron star mergers, however, generate thousands of times more heavy elements per event. Combine this with the fact that mergers eject their metallic bounty at higher velocities, spreading it farther across galactic neighborhoods, and the math becomes undeniable. Supernova might light up the cosmos, but kilonovae quietly stock it with treasure. Yet supernovae still play a crucial supporting role in this cosmic drama. Their explosions create the neutron stars that eventually collide, and their shockwaves help mix freshly minted heavy elements into interstellar clouds. Some theories even suggest a hybrid model. Certain supernovae might birth magnetars, neutron stars with magnetic fields so intense they mimic miniature kilonovae during their formation. These extreme stellar magnets could contribute a secondary R-process production line, though their output pales next to full neutron star mergers. The ultimate proof comes from our own solar system's composition. Meteorites show precise ratios of platinum group metals that match neutron star merger models to within 1%. Level of agreement supernovae can't approach. Even more telling, these ratios hold constant across the galaxy's oldest and youngest stars, suggesting neutron star collisions have been producing heavy elements with factory-like consistency for 12 billion years. Supernova may be the universe's flashy pyrotechnics, but kilonovae are its meticulous jewelers, crafting precious metals with a precision no other cosmic event can match. This division of stellar labor solves one of astronomy's oldest puzzles: why Earth has just the right mix of heavy elements for life and technology. Without neutron star collisions, our planet might have ended up with plenty of iron, but no gold for electronics, no uranium for geothermal heat, no platinum for industrial catalysts. The universe balances its budgets in mysterious ways. Supernova provide the bulk materials, but it takes the rarest, most violent collisions to sprinkle in the elements that make planets truly special. Every time you use a device containing rare earth metals or admire a piece of gold jewelry, you're holding a piece of this cosmic partnership, a testament to how the universe's most destructive events create its most enduring gifts. Scientists don't need a time machine to witness the alchemy of neutron star collisions. They recreate it right here on Earth using some of the most advanced laboratories ever built. At facilities like the National Ignition Facility in California or the GSI Helmholtz Center in Germany, researchers simulate the extreme conditions of merging neutron stars by firing powerful lasers at tiny targets or smashing atomic nuclei together at nearly light speed. These experiments last mere nanoseconds, but within that blink of an eye, they replicate temperatures exceeding 100 million degrees and pressures found nowhere else on our planet, conditions so brutal they momentarily transport us inside a kilonova's fiery heart. One groundbreaking approach uses high-energy lasers to compress materials to neutron star densities. Picture this: 192 laser beams converge on a gold capsule smaller than a peppercorn, delivering a pulse with 500 trillion watts of power, more than the entire United States uses at any instant. The capsule implodes, creating a plasma hotter than the Sun's core where electrons get ripped from atoms, mimicking the neutron-rich environment where the R process occurs. By analyzing the resulting nuclear reactions with gamma-ray spectrometers, scientists can track how neutrons rapidly attach to nuclei, the first step toward forming heavy elements like gold. Particle accelerators offer another window into cosmic alchemy, when physicists at the facility for rare isotope beams accelerate uranium nuclei to 90% light speed and slam them into beryllium targets. They create short-lived isotopes that decay in patterns identical to those predicted in neutron star mergers. These fleeting atomic configurations, some lasting mere milliseconds, are the same overweight nuclei that would eventually shed neutrons to become stable precious metals in space. It's like catching a frame-by-frame replay of the universe's most exclusive jewelry-making process. Recent breakthroughs have come from studying waiting point nuclei-specific atomic configurations that act as bottlenecks in the R process chain. In 2023, an experiment at CERN ISOLD facility isolated isotopes of tin-132, a crucial stepping stone between lighter elements and heavy metals. By precisely measuring how quickly this isotope captures neutrons, researchers confirmed theoretical models showing how the R process builds elements faster than they can decay, like adding floors to a skyscraper while the lower levels are still under construction. The challenges of these experiments are as extreme as the phenomena they study. Researchers must account for quantum effects that alter nuclear reaction rates at different temperatures, while detectors must operate amidst radiation levels that would fry conventional electronics. Some teams now use diamond sensors that can withstand the intense gamma-ray bursts produced during these microcosmic kilonovas. Others employ machine learning to sift through terabytes of collision data, searching for the telltale signatures of element formation. What makes this laboratory alchemy so revolutionary is how it bridges the gap between astronomical observations and atomic physics. Before these experiments, astrophysicists relied on theoretical models with huge uncertainties about nuclear properties. Now, by recreating slices of neutron star conditions, they can test which nuclear reactions actually occur, tightening the cosmic recipe for gold. The results have already overturned assumptions, revealing that some elements form more efficiently than predicted, while others require even more extreme environments. Perhaps most remarkably, these experiments help explain puzzling observations from space. When the neutron star merger GW170817 produced less europium than expected, lab measurements revealed its formation depends critically on the neutron density's exact fluffiness, a parameter impossible to deduce from telescopes alone. This synergy between cosmic cataclysms and tabletop physics is rewriting our understanding of where and how the universe's rarest elements come into being. The next frontier involves even more precise recreations. Upcoming facilities like the Facility for Antiproton and Ion Research will simulate merger conditions for longer durations, allowing scientists to trace the R process deeper into heavy element territory. Other teams are developing techniques to study nuclear reactions in magnetized plasmas, closer mimics of the chaotic magnetic fields surrounding colliding neutron stars. With each experiment, we're not just uncovering the secrets of cosmic gold, we're learning to speak the universe's elemental language, one neutron at a time. That gold ring on your finger or the tiny contacts in your smartphone aren't just human inventions. They are fragments of a cosmic disaster older than Earth itself. Every shimmering bit of gold humanity has ever touched carries atomic echoes of colliding neutron stars, a heritage written in the very fabric of these metals. Consider this. The wedding band you might be wearing right now contains atoms that survived a journey spanning billions of years, flung across space at relativistic speeds before finally finding their way into Earth's crust. It's not poetry, it's physics. Electronics reveal an even deeper connection. A typical smartphone contains around 30 milligrams of gold, primarily in its circuitry. These microscopic traces are more than just conductive, they're cosmic refugees. Unlike iron or aluminum, forged in common stellar furnaces, gold's atomic structure betrays its extraordinary origin. Each gold nucleus, with its 79 protons, is so densely packed that only the neutron-rich maelstrom of a kilonova could have assembled it. The gold wires in your device don't just carry electricity, they carry the legacy of the universe's most violent alchemy. Dental fillings offer another unexpected link to the stars. Gold's resistance to corrosion makes it ideal for enduring the wet, acidic environment of the human mouth, a property rooted in atomic bonds formed during its neutron star birth. When your dentist presses gold into a tooth, they're using material that once swirled in a superheated disk around a newborn black hole. Even the platinum in catalytic converters, silently scrubbing pollutants from car exhaust, owes its existence to the same process that filled the cosmos with heavy elements. The scale of this cosmic recycling is almost unimaginable. All the gold ever mined by humanity would fit into 3 Olympic-sized swimming pools, a minuscule fraction of what arrived on Earth during its formation. Most sank to the core, leaving scattered traces in the crust that we've painstakingly extracted over millennia. Yet every ounce represents atoms that outlasted supernova, survived interstellar space, and endured planetary collisions before becoming concentrated enough for us to discover. Perhaps most astonishing is how recently science uncovered this connection. Until the 21st century, gold's origin remained one of astronomy's great unsolved mysteries. Ancient cultures mythologized it as tears of the sun or God's flesh, while alchemists wasted centuries trying to conjure it from base metals. The truth, that it required the death spiral of 2 ultra-dense stellar corpses, proves far more spectacular than any legend. Modern mining operations might extract gold from rock, but the real miners were neutron stars, scattering their metallic harvest across the galaxy eons before humans walked the Earth. This transforms how we see ordinary objects. A gold necklace isn't just adornment, it's wearable astronomy. The plating on astronaut helmets isn't merely functional, it's stardust repurposed for space exploration. Even the thin gold films shielding spacecraft from solar radiation mirror the metal's ancient role, protecting Earth-bound atoms now returning to the cosmos. The universe forged these elements in chaos, but they've become tools of human ingenuity, bridging the gap between stellar cataclysms and everyday life. So next time you handle anything containing gold or platinum, pause for a second. You're touching material older than the sun, rarer than diamonds, and forged under conditions no laboratory could replicate. These metals connect you to events so distant in time and space. They defy comprehension, yet they're right there in your pocket, on your wrist, or even in your teeth. Humanity didn't create gold. We simply discovered it, mined it, and reshaped it. Its true creators died billions of years ago, in collisions that lit up the darkness, leaving behind atomic treasure waiting for civilizations like ours to find. While neutron-star collisions create cosmic gold, black hole mergers are the universe's ultimate dead ends when it comes to heavy element production. The difference boils down to what gets left behind and what escapes into space. When two black holes spiral together, they vanish behind an event horizon so intense that not even light can escape, leaving no debris to enrich the cosmos. These mergers shake spacetime with gravitational waves, but they don't produce the neutron-rich fireworks needed to forge gold or platinum. It's like comparing a silent vacuum to an exploding fireworks factory. Both are dramatic, but only one leaves behind anything useful. Black holes are cosmic hoarders. Their immense gravity traps everything nearby, including any potential material that could form heavy elements. Even if two black holes shred each other's accretion disks during a merger, the resulting tidal forces heat the material to extreme temperatures, but it all ultimately gets swallowed. There's no equivalent to the neutron-rich debris cloud ejected during a neutron-star collision. Simulations show that even in rare cases where black holes might harbor neutron-rich matter from earlier meals, their mergers typically produce only faint thermal flares rather than the R-process element factories we see with neutron stars. The mass gap between these events tells another revealing story. Neutron stars max out at around 2.5 times the Sun's mass before collapsing into black holes, a sweet spot where collisions release just enough debris to escape gravity's grasp. Black hole mergers, on the other hand, involve objects so massive that their event horizons are far larger, leaving little room for material to avoid falling in. The lightest known black hole merger involved objects 6 times heavier than our Sun, each with gravity so strong that any potential heavy elements would be sucked into oblivion long before they could form. Yet nature occasionally throws a curveball. Some theoretical models suggest that if a neutron star and black hole merge in just the right way, with the black hole relatively small and spinning fast, the neutron star might be shredded before being entirely consumed. Such events could produce faint kilonova-like signals with some R-process elements, but these would be cosmic oddities rather than major contributors to the galaxy's heavy element budget. The gold in your jewelry almost certainly comes from pure neutron star collisions, not these rare hybrid mergers. Astronomers have another way to confirm this cosmic dichotomy by studying the light shows these events produce or don't. Every neutron star merger observed so far, from GW 170817 to more recent detections, has produced brilliant optical and infrared afterglows from decaying heavy elements. Black hole mergers, radio silence. Even when LIGO detects gravitational waves from black holes colliding every few weeks, telescopes find absolutely nothing in the corresponding patch of sky. No glowing debris, no gamma-ray bursts, just empty space where two gravitational monsters vanished without a trace. This isn't to say black hole mergers aren't fascinating. They're crucial for testing general relativity and understanding how the most massive objects in the universe evolve. But when it comes to manufacturing the elements that make up our world, neutron-star collisions are the undisputed champions. The universe is strangely selective about where it places its treasure factories, favoring the violent embrace of dead stars over the silent consumption of black holes. Every time you use a device that relies on rare earth metals or admire a piece of gold jewelry, you're holding proof that sometimes destruction isn't the end, it's the beginning of something precious. The fate of two merged neutron stars isn't just a question of what remains. It's a cosmic cliffhanger where milliseconds determine whether the universe gets a new black hole or an exotic stellar zombie. When these ultra-dense objects finally collide, the resulting object teeters on the knife edge of physics, with its destiny hanging on a single variable, mass. Cross a critical threshold, and the merged core collapses instantly into a black hole. Stay just below, and you might get the most bizarre star in existence, a hypermassive neutron star that defies everything we know about matter. Let's start with the most common outcome, the birth of a black hole. Current models suggest that if the combined mass of the merging neutron stars tips over about 2.8 times the Sun's mass, gravity wins instantly. In less time than it takes light to cross a city block, the merged core shrinks past the point of no return, forming a black hole with an accretion disk of swirling debris. But here's the twist: not all this material falls in immediately. For up to a second, the doomed core might resist collapse through a phenomenon called differential rotation, where the inner regions spin faster than the outer layers, buying precious milliseconds for heavy elements to escape before the event horizon seals everything away. Then there's the wild card hypermassive neutron stars. These temporary monsters exist in a quantum limbo, packing up to 3 solar masses into a sphere barely 20 kilometers wide. They shouldn't exist according to textbook physics. Neutron degeneracy pressure alone can't support that much weight. But for a few hundred milliseconds to potentially minutes, rapid spin and extreme temperatures provide extra support against collapse. Picture a spinning top balanced on a needle. It stays upright through sheer momentum, but the slightest instability sends it crashing down. These ephemeral stars are the universe's ultimate tightrope walkers, flickering into existence just long enough to shape the Kilonova's light curve before vanishing into oblivion. The rarest outcome, a stable supramassive neutron star. If the merger's total mass stays just below the collapse threshold and the resulting object spins fast enough, centrifugal force might permanently counteract gravity. This creates a pulsar on steroids, a magnetar with a magnetic field 1,000 times stronger than ordinary neutron stars, beaming radiation across the cosmos like a celestial lighthouse. GW-170817's aftermath hinted at this possibility when X-ray observations detected a lingering glow months after the merger, potentially from a newborn magnetar energizing the debris field. What makes these outcomes so consequential is how they sculpt the Kilonova explosion itself. A prompt black hole produces a shorter, dimmer blast with less heavy element production, since most debris gets swallowed too quickly. Hypermassive neutron stars extend the fireworks, allowing more neutron-rich material to escape and forge gold. Stable remnants might not produce classic kilonovae at all. Instead, their relentless energy output could power glowing magnetar nebulae that mask the R-process signature entirely. The smoking gun for these scenarios lies in gravitational waves. The frequency and duration of the merger's chirp reveal whether the merged object survived or collapsed immediately. Data from GW-170817 suggested a brief hypermassive neutron star formed before collapsing, a Goldilocks scenario that explains both the explosion's brightness and the abundance of ejected heavy elements. Future detectors like the Einstein telescope aim to catch even subtler vibrations, potentially hearing the moment a hypermassive star finally buckles under its own weight. Perhaps the most mind-bending possibility is the formation of a quark star, a hypothetical state where neutrons themselves break down into their component, quarks, under the merger's insane pressures. This cosmic alchemy would produce an object denser than anything in the known universe, with a surface harder than diamond and gravity so intense it bends light into knots. While no confirmed quark stars exist yet, some theorists argue certain ultraluminous supernovae might actually be quark star births in disguise. In the end, neutron star mergers are the universe's ultimate transformers, taking two dead stars and forging something entirely new. Whether they leave behind black holes, magnetars, or something even stranger, these collisions don't just create heavy elements, they rewrite the rules of physics itself. Every gold atom floating through space is a tiny relic of this celestial metamorphosis, a reminder that even in destruction, the universe finds ways to build anew. Our solar system's precious metals might trace their origins to multiple apocalyptic events scattered across the Milky Way's history, based on the staggering amount of gold, platinum, and other R-process elements present in Earth's crust and meteorites. Astrophysicists estimate between 10 to 20 neutron star collisions likely contributed to our local cosmic neighborhood's elemental wealth. These catastrophic mergers didn't happen all at once, they occurred in waves spanning billions of years, each explosion scattering its metallic bounty across the galaxy like a series of timed cosmic treasure chests waiting to be incorporated into future star systems. The earliest contributors to our solar system's gold reserves likely detonated when the Milky Way was just a toddler. Chemical analysis of ancient metal-poor stars reveals the first R-process elements appeared roughly 1 billion years after the Big Bang, meaning the very first generation of neutron star collisions occurred when galaxies were still assembling themselves. These primordial mergers created foundational heavy elements that became building blocks for subsequent stellar generations. Fast forward to about 7 billion years ago, when our galactic neighborhood experienced what astronomers call the R-process enhancement epoch, a period when neutron star mergers peaked in frequency due to the optimal age of massive binary star systems reaching their dramatic end stages. The most recent contributors to Earth's gold might have exploded relatively close to home, both in space and time. Advanced simulations tracking the motion of interstellar clouds suggest one particularly rich merger occurred within 300 light-years of our future solar system's birthplace, just 100 million years before the Sun ignited. This cosmic timing was crucial, close enough that debris hadn't dispersed too thinly through the galaxy, yet distant enough to allow proper mixing with the molecular cloud that birthed our solar system. The radioactive isotopes found in meteorites act like atomic stopwatches, confirming some heavy elements arrived freshly minted on a cosmic timescale, their decay products still detectable after 4.6 billion years. What's astonishing is how these events collectively seasoned our solar system's birth cloud. Imagine the Milky Way as a giant soup pot, with each neutron star collision adding a pinch of precious metal seasoning. Early mergers provided base notes, older elements thoroughly mixed through the galaxy. Later, local explosions added brighter flavor notes, concentrated pockets of recently forged metals that hadn't had time to fully disperse. By the time our solar nebula collapsed, it inherited this layered legacy, explaining why meteorites show slightly different R-process element ratios depending on when their parent asteroids formed during planetary construction. The implications stretch beyond mere chemistry. Without this staggered enrichment process, Earth might have ended up with either too few heavy elements for a metallic core to generate our protective magnetic field, or so many that toxic radioactive elements made the surface uninhabitable. Instead, we got a Goldilocks mixture, just enough gold for technology, sufficient uranium for geothermal heat, and adequate platinum group metals to catalyze prebiotic chemistry. This cosmic balancing act depended entirely on neutron-star mergers occurring at the right places and times across galactic history, making our solar system's elemental cocktail the result of perfect celestial timing spanning billions of years. While we'll never know the exact number of collisions that contributed to Earth's gold, each one left faint fingerprints in the atomic makeup of our planet. Some gold atoms might remember the shockwaves of the very first mergers in the young universe, while others carry the signature of more recent, localized cataclysms. Together, they form an inheritance more valuable than any treasure, a direct material connection to the most violent and creative events in cosmic history. The next decade promises to revolutionize our understanding of neutron-star collisions, thanks to an upcoming generation of observatories designed to catch these cosmic fireworks in unprecedented detail. Leading the charge is the Laser Interferometer Space Antenna, or LISA, a gravitational wave detector so sensitive it could hear the chirp of colliding neutron stars across the entire observable universe. Unlike ground-based detectors like LIGO that catch high-frequency waves from the merger's final seconds, LISA's space-based system will detect low-frequency ripples starting weeks before impact, giving astronomers their first ever early warning system for these events. Picture getting a celestial heads-up that two neutron stars are spiraling toward doom, with enough time to point every telescope on Earth at the right patch of sky before the explosion even happens. Then there's the Vera Rubin Observatory, currently under construction in Chile, which will scan the entire visible sky every few nights with a camera so powerful it could spot a golf ball on the moon. This relentless cosmic surveillance means we'll catch dozens of kilonovae each year instead of once in a lifetime. Rubin's real superpower lies in its ability to spot the afterglow of neutron-star mergers across multiple wavelengths simultaneously, from ultraviolet to infrared, revealing not just where heavy elements form, but how they cool and disperse through space. But the future toolkit doesn't stop there. The Square Kilometer Array Radio Telescope will map the aftermath of collisions in exquisite detail, tracking how ejected material plows through interstellar gas over years. NASA's upcoming Nancy Grace Roman Space Telescope will peer through dust clouds that obscure visible light, uncovering hidden kilonovae in distant galaxies. And next generation, spectrographs like those planned for the European Extremely Large Telescope will break down the light from these explosions atom by atom, creating chemical fingerprints that reveal exactly which heavy elements formed in each event. Perhaps most exciting are the wildcard possibilities. Dark matter detectors like LZ and Xeno-NNT might accidentally spot signals from neutron star mergers. Their ultra-sensitive equipment could pick up exotic particles flung out during collisions. Even neutrino observatories like IceCube could get in on the action, potentially detecting bursts of these ghostly particles released in the merger's chaotic first milliseconds. Every new instrument adds another dimension to our understanding, turning what was once a blurry snapshot into a high-definition movie of cosmic alchemy in action. These advancements will answer lingering mysteries. Do all neutron star collisions produce the same mix of elements, or are there galactic gold mines where certain mergers create richer deposits? How often do these events leave behind exotic remnants like quark stars? And could some heavy elements come from entirely different sources, like colliding white dwarfs or magnetar flares? The data pouring in from these observatories won't just fill textbooks, it could rewrite them, revealing how the universe's rarest elements travel from stellar catastrophes to our everyday lives. What makes this new era extraordinary is how these tools will work together. A gravitational wave alert from LISA could trigger Rubin to find the optical counterpart, while the James Webb Space Telescope analyzes its infrared spectrum and radio telescopes monitor long-term evolution. This multi-messenger approach, combining gravity waves, light, and particles, will give us what astronomers call the full picture of neutron-star collisions for the first time. We're not just building better telescopes, we're constructing an interconnected web of cosmic surveillance that will watch the universe's heaviest elements being forged in real time. The implications stretch far beyond astronomy. Understanding exactly how and where gold forms could one day guide asteroid mining missions, helping target metal-rich space rocks that originated from ancient neutron star debris. Pharmaceutical researchers are even studying how gold nanoparticles formed in space might have unique biomedical properties. Every new observation brings us closer to answering fundamental questions. How rare is Earth's particular mix of precious metals? Are other solar systems out there with 10 times our gold reserves, or none at all? The answers will reshape our understanding of cosmic chemistry and planetary habitability. As these observatories come online, we stand on the brink of discoveries we can barely imagine. The same cosmic violence that filled Earth with life-enabling heavy elements is still happening across the universe. We're just now building the tools to watch it unfold in real time. Soon, neutron star collisions won't be theoretical models or rare surprises, but regular celestial events we can study like weather patterns. And with each new detection, we'll peel back another layer of the universe's grand recycling program, where death and rebirth on a cosmic scale create the very stuff of planets, life, and human civilization. The idea of a neutron star collision near Earth sounds like something ripped from a doomsday movie, a cosmic catastrophe unleashing deadly gamma rays and gravitational tsunamis across our planet. But before you start building an underground bunker, here's the reassuring truth. The universe has already rigged the game in our favor. For a neutron star merger to pose any threat, it would need to happen absurdly close by cosmic standards within a few dozen light-years of Earth. To put that in perspective, the Milky Way spans 100,000 light-years, and the nearest known neutron star pair is over 1,000 light-years away. Even at that distance, the effects would be negligible. Gamma-ray bursts, the universe's most powerful explosions, are the primary concern during these mergers. A direct hit from one of these energy beams could strip Earth's ozone layer, triggering mass extinctions, but neutron star collisions produce tightly focused jets of radiation, like celestial blowtorches. The odds of Earth being in the crosshairs are astronomically low. We'd need to be both dangerously close and perfectly aligned, a cosmic bullseye with worse odds than winning the lottery while being struck by lightning. And even if we were that unlucky, the universe gives us a built-in warning system. Gravitational wave detectors would sense the approaching disaster hours before the gamma rays arrived, giving humanity time to shield critical infrastructure. What about the gravitational waves themselves? While mergers shake spacetime with the power of a quadrillion suns, their ripples fade rapidly over distance. By the time they reach Earth, they'd stretch and squeeze our planet by less than the width of an atom, utterly harmless. The real danger isn't from the collision, but from its aftermath. Kilonova spew radioactive debris at relativistic speeds, yet this material takes millions of years to traverse interstellar space. Any heavy elements headed our way from past mergers are already here, safely embedded in Earth's crust or floating harmlessly as space dust. History backs up our safety. Over 4 billion years, Earth has endured countless cosmic threats, asteroid impacts, supernova, gamma-ray bursts, yet neutron star collisions left no visible scars in our geological record. The last nearby merger likely occurred over 100 million years before our solar system formed, its metallic contributions arriving as microscopic stardust rather than apocalyptic radiation. Even if one happened tomorrow in our galactic neighborhood, the vast emptiness between stars acts as nature's perfect buffer. The universe operates on a scale that defies human intuition. Events capable of sterilizing planets occur regularly across the cosmos, but the distances involved make Earth's existence remarkably safe. Neutron star collisions aren't celestial predators, they're distant artists, painting the galaxy with precious metals from light years away. The gold in your jewelry proves these explosions enrich rather than destroy, delivering their gifts across eons without harming a single living cell. So while the cosmos thrives on violence, we're privileged to witness its beauty from the safest seats in the universe. Gold isn't just rare on Earth, it's one of the universe's scarcest treasures, scattered so thinly across the cosmos that all the gold ever mined would form a cube barely 20 meters wide if gathered together. Yet this precious metal exists almost everywhere we look, from the atmospheres of distant exoplanets to the cores of ancient stars in far-flung galaxies. The Milky Way alone likely holds over 20 billion times Earth's mass in gold, but here's the catch: that gold isn't piled in cosmic vaults. It's dissolved in interstellar gas, locked inside asteroids, or sunk to the cores of planets where no drill could ever reach. Exoplanets add fascinating twists to this cosmic treasure hunt. Astronomers have detected traces of heavy metals in the atmospheres of ultra-hot gas giants called hot Jupiters, where temperatures exceed 2,000 degrees Celsius, hot enough to vaporize gold into gaseous form. On the night side of these blazing worlds, that gold might literally rain from the sky as liquid metal droplets. Other star systems could harbor even stranger gold deposits. Imagine diamond planets, with cores of crystallized carbon, their mantles laced with veins of pure gold forged in ancient neutron star collisions. Distant galaxies tell an even more dramatic story. When the Hubble Space Telescope examined the glow of the most distant quasars, it found spectral signatures of gold and other heavy elements in light that had traveled nearly 12 billion years to reach us. This means the universe was already minting gold when it was less than 2 billion years old, proof that neutron star collisions began enriching the cosmos almost as soon as the first stars died. Some elliptical galaxies show particularly rich concentrations of these metals, likely due to frenzied merger activity in their youth that triggered waves of neutron star collisions. The real cosmic jackpots might lie in globular clusters, ancient, densely packed groups of stars orbiting galaxies like celestial beehives. These clusters contain some of the oldest stars in the universe, many born from gas clouds enriched by multiple generations of neutron star mergers. Simulations suggest a single globular cluster could contain thousands of gold-rich asteroids formed before Earth existed, their surfaces studded with precious metal nuggets the size of houses. If humanity ever develops interstellar mining technology, these clusters might be our first stop. Yet for all its cosmic abundance, gold remains tantalizingly out of reach. Most of it sank to Earth's core during our planet's molten youth, leaving only trace amounts in the crust, like crumbs from a feast we'll never attend. The same process likely occurred on Mars, Venus, and Mercury, meaning every rocky planet probably hides a fortune in its depths that no civilization will ever extract. Even if we could mine other star systems, nature's distribution system ensures gold will always be rare where it's accessible and abundant where it's not. A cosmic irony written in Neutron star ash. The grandest gold reserves might not be on planets at all. Some white dwarf stars, the smoldering cores of dead sun-like stars, show spectral evidence of heavy metals in their atmospheres. These aging stars likely consumed gold-rich planets in their death throes, dissolving entire worlds into their atmospheres like sugar in tea. One particularly bizarre white dwarf, 200 light-years away, appears to have swallowed a planet so metal-rich that its outer layers now contain enough gold to gild every continent on Earth 10 times over. This celestial gluttony offers a sobering perspective. The universe's greatest gold hoards might exist inside stars that destroyed their own planets to acquire them. What makes this cosmic accounting truly mind-bending is the scale of waste. For every atom of gold that ends up in a smartphone or wedding band, trillions more were lost to interstellar space or locked forever in stellar graves. The universe creates gold through violence, then scatters it with indifference, a paradox that makes our ability to gather even tiny amounts all the more remarkable. Whether floating in gas clouds between galaxies or buried in the hearts of dead stars, gold's journey reminds us that rarity isn't just about quantity, it's about the extraordinary series of events required to bring it within our reach. Spotting a kilonova in action requires astronomers to become cosmic detectives, piecing together clues across the electromagnetic spectrum and beyond. Unlike supernova that blaze for weeks, these neutron-star merger afterglows fade within days, a fleeting cosmic signal demanding lightning-fast coordination. The hunt begins with gravitational wave observatories like LIGO and Virgo, acting as the universe's early warning system. When their sensitive lasers detect spacetime ripples matching neutron stars' telltale spiraling frequency, automated alerts blast to telescopes worldwide within seconds. But here's the catch: gravitational waves alone can't pinpoint the explosion's location. The signal might narrow it down to an area of sky 300 times larger than the full moon, forcing observatories to play a high-stakes game of celestial hide and seek. Modern sky surveys like the Zwicky Transient Facility revolutionized this search by scanning entire visible skies nightly. Their ultra-sensitive cameras compare new images with previous ones, flagging any sudden bright spots that could be kilonovae. The key identifier: these explosions don't behave like anything else in space. Within hours of detection, their light shifts from blistering blue, caused by decaying radioactive lanthanides, to deep red as heavier elements like gold dominate the spectrum. This chromatic metamorphosis happens 5 times faster than a supernova's evolution, creating a light fingerprint unlike any other cosmic event. Spectroscopy transforms these colorful flashes into elemental treasure maps. When astronomers analyzed light from GW 170817's kilonova, they spotted absorption lines matching tellurium and cesium, smoking gun evidence of rapid neutron capture in action. More recent observations revealed even heavier elements like strontium and europium forming in real time, confirming predictions about the R process's step-by-step atomic assembly line. Each element leaves unique spectral signatures, allowing scientists to reconstruct the kilonova's chemical output like forensic scientists analyzing ash after an explosion. The real game-changer has been multi-messenger astronomy, combining gravitational waves, light, and sometimes even neutrinos to study single events. This approach turns kilonovae into cosmic Rosetta Stones, helping decode how the universe builds heavy elements. For example, the gravitational wave signal reveals the neutron star's masses before collision, while the light curve shows how much material escaped. Compare the two, and you can calculate exactly how efficient the merger was at producing gold versus black hole fuel. Some events eject up to 10% of their mass as precious metals, while others barely any variability that might depend on whether the merged core collapsed immediately or lingered as a hypermassive neutron star. These discoveries rewrite our understanding of cosmic chemical evolution. Before 2017, astronomers assumed supernova dominated heavy element production. Now, kilonova observations prove neutron star collisions contribute nearly all the universe's gold, half its platinum, and most elements heavier than iodine. Ancient stars in our galaxy's halo show this transition clearly. Their atmospheres preserve elemental ratios matching pure supernova output early on, then suddenly spike with R-process elements as neutron star mergers became frequent enough to enrich interstellar gas. It's as if the universe took 1 billion years to perfect its gold-making recipe, with kilonovae as the master chefs. The Holy Grail now lies in catching a kilonova's earliest moments, something no telescope has achieved yet. Current records show events several hours post-merger, missing the critical first minutes when most heavy elements form. New projects like the Black Gem Array in Chile aim to fix this by scanning gravitational wave alert regions within minutes. Others plan to train machine learning algorithms on simulated kilonova light curves, helping robotic telescopes recognize these events faster than any human could. The payoff: witnessing the exact moment free neutrons begin assembling into gold nuclei, a process that currently exists only in supercomputer simulations. Every kilonova spotted adds another piece to this cosmic puzzle. Some appear remarkably similar, while others, like the curiously red kilonova in galaxy NGC 4993, defy expectations with unusual light curves hinting at exotic physics. These outliers might involve neutron stars with extreme magnetic fields or unexpectedly high masses that tweak the R-process recipe. With each new detection, astronomers refine their models of how neutron-rich matter behaves under conditions impossible to recreate on Earth, turning these distant explosions into laboratories for nuclear physics. The search continues to push technological limits. Proposed space telescopes like the Transient Astrophysics Probe would monitor the entire sky continuously in ultraviolet, ideal for catching kilonovae's initial blue flash. Meanwhile, next-generation gravitational wave detectors like Cosmic Explorer promise to hear neutron star mergers across the entire observable universe, potentially spotting dozens per year. This incoming flood of data will finally answer lingering questions. Do all kilonovae produce the same mix of elements? Could some heavy metals come from even rarer events? And how did the very first neutron star collisions in the early universe seed galaxies with the ingredients for planets like Earth? Already, these discoveries transform how we see our place in the cosmos. The gold in ancient Egyptian tombs, the platinum in catalytic converters, even the uranium powering cities, all were forged in explosions witnessed only recently by science, yet occurring since time began. Kilonovae aren't just cosmic spectacles, they're the universe's primary architects of rarity, turning stellar graveyards into treasure chests one collision at a time. With every new detection, we're not just observing distant cataclysms, we're decoding the origin story of everything heavy, precious, and enduring in our world. The gold in your jewelry and the uranium in nuclear reactors might seem like cosmic luxuries, precious, but ultimately unnecessary for life. But what if these heavy elements from neutron star collisions played a far deeper role in shaping habitable worlds? The universe's most violent explosions could be silent architects of life itself, scattering not just glittering metals, but essential ingredients for biology across the galaxy. Take Earth's molten core, where uranium and other radioactive elements act as a natural nuclear furnace. This subsurface heat engine drives plate tectonics, the geological recycling system that regulates our climate over millennia. Without these heavy elements simmering beneath our feet, Earth might have cooled into a stagnant, lifeless rock like Mars. The same uranium that powers cities today also helped maintain our planet's magnetic field for billions of years, shielding early life from lethal cosmic radiation. It's a staggering thought. The same cataclysms that forged gold may have inadvertently provided the steady warmth and protection that allowed life to take root. Then there's the biological magic of rare earth metals. Molybdenum, a heavy element almost exclusively produced by the R process, plays a starring role in nitrogen-fixing enzymes, proteins, that allow plants to turn atmospheric nitrogen into usable nutrients. Without this neutron star byproduct, Earth's ecosystems might lack the fertility to support complex life. Similarly, iodine, another R process element, is essential for thyroid function in animals, while europium and other rare earths are critical for photosynthesis in marine plankton. These elements didn't just arrive on Earth by chance, they were delivered in precisely the right proportions by ancient stellar collisions, like a cosmic care package preloaded with life's building blocks. The distribution of these elements across planets adds another layer of intrigue. Astronomers studying exoplanets have found worlds with tantalizing imbalances, some with 10 times Earth's platinum group metals, others nearly devoid of heavy elements entirely. This cosmic lottery could determine which planets develop protective magnetic fields, nutrient-rich soils, or even the right chemistry for DNA to form. A world without neutron star debris might lack the conductive metals needed for neural activity, or the catalytic surfaces that speed up prebiotic chemical reactions. We could be living in a Goldilocks zone not just for temperature, but for elemental abundance, a planet that won the interstellar jackpot when it comes to heavy metal inheritance. Perhaps most remarkably, these elements might have guided life's earliest evolutionary steps. Deep-sea hydrothermal vents, where many scientists believe life began, are lined with iron-sulfur minerals that catalyze organic reactions. But newer research shows vents rich in R-process metals like nickel and cobalt could have been even more efficient at assembling complex molecules. The same gold nanoparticles we use in medicine today might have served as primitive electron shuttles for Earth's first metabolic processes. Even the zinc in your immune system traces back to neutron star collisions, a reminder that our biology is literally written in stardust, forged by stellar catastrophes. This raises a profound question: is life itself a consequence of these violent events? If neutron star mergers hadn't peppered our galactic neighborhood with heavy elements, would Earth have remained a barren rock? The universe seems to operate on a principle of destructive creation, where the things that tear stars apart also build the foundations for biology. Every heartbeat, every thought, every ecosystem on our planet owes something to explosions that occurred billions of years before the sun ignited. We're not just made of star stuff, we're made of the rarest, most violently produced star stuff in existence. Future discoveries might reveal even deeper connections. Some astrobiologists speculate that planets with higher concentrations of neutron star debris could evolve life with radically different biochemistries, perhaps using platinum instead of iron in blood, or gold-based enzymes for photosynthesis. Others suggest these heavy elements could be key to detecting life elsewhere. Imagine telescopes spotting the spectral signature of molybdenum-rich enzymes in an exoplanet, its atmosphere as a biosignature. One thing is certain as we explore the cosmos: we're not just searching for life, but for the elemental legacies of neutron star collisions that make life possible. The same explosions that crafted our planet's metallic heart might have written the universal recipe for biology itself. For all our breakthroughs in understanding neutron star collisions, these cosmic events still guard profound mysteries, puzzles that remind us how much we don't yet know. Take the R process, that lightning-fast nuclear chain reaction responsible for forging gold and other heavy elements. While we've recreated slivers of it in labs and modeled it in supercomputers, the exact sequence of atomic transformations remains hazy. Imagine trying to reconstruct a fireworks display by studying just a few scattered ashes. That's the challenge physicists face when tracing how free neutrons assemble into elements like platinum or uranium in mere seconds. One persistent enigma is the waiting point problem. During the R process, certain atomic configurations act like traffic jams, nuclei, that resist adding more neutrons until they decay. The precise isotopes involved and how they influence the final elemental mix vary wildly based on conditions we can't yet measure directly in mergers. It's like baking a cake where the recipe changes depending on oven temperature, but the oven exists for only a millisecond in a galaxy far away. Recent lab experiments with tin-132 isotopes revealed surprises. Some nuclei capture neutrons far faster than predicted, suggesting the R process might produce heavier elements more efficiently than our models assume. Even more puzzling is the wild variability in observed kilonovae. Some eject material glowing predominantly blue, indicating lighter, heavy elements like silver, while others burn red with gold and platinum signatures. Does this mean neutron star collisions come in different flavors, depending on the star's initial masses or rotation speeds? Or could some heavy elements escape detection because they form deeper in the explosion, hidden beneath outer layers of debris? The answer might lie in gravitational wave data. We're not yet collecting subtle vibrational clues about the merged object's density and spin that current detectors miss. Then there's the cosmic accounting problem. When astronomers tally up all the gold in the Milky Way and divide it by the estimated rate of neutron star mergers, the numbers almost match, but not quite. Some theories suggest alternative R process sites, like magnetar births or colliding white dwarfs, might contribute a small percentage. Others propose we're underestimating merger frequencies. Perhaps binary neutron stars form more often in dense star clusters we haven't fully surveyed. The James Webb Space Telescope's infrared eyes might soon spot ancient kilonovae in distant galaxies, helping us recalculate the universe's heavy element budget. The greatest unknown: what happens in the first milliseconds after collision, the quantum realm where neutron star material transitions from familiar matter to exotic states we can't replicate on Earth. Some theories predict temporary quark soup, where neutrons dissolve into their fundamental particles. Others suggest superfluid phases or even strange matter that converts ordinary atoms into bizarre stable forms. Without gravitational wave detectors sensitive enough to capture these infinitesimal tremors, or telescopes fast enough to catch the explosion's earliest light, we're left theorizing about processes that could rewrite nuclear physics. This isn't just academic curiosity. Each unanswered question ripples through our understanding of cosmic history. If neutron star mergers were more frequent in the early universe, they might have seeded the first galaxies with gold sooner than we thought, potentially influencing how early planets formed. Alternatively, if some mergers produce entirely unexpected elements, we might need to rethink how radioactive isotopes heat planetary cores, or even how life's building blocks scatter through space. Every kilonova we observe is a Rosetta Stone waiting to be decoded, holding clues not just about stellar death, but about the very origins of everything tangible in our lives. The humility these mysteries instill is perhaps their greatest gift. For all our advanced tools, we're still piecing together the universe's most violent alchemy from fleeting signals and scattered atomic traces. Each discovery peels back a layer, revealing deeper questions beneath. Reminder that the cosmos guards its grandest secrets with equal parts fury and elegance. While gold captures the spotlight, neutron star collisions unleash cosmic oddities far stranger than precious metals phenomena that push the laws of physics to their breaking point. Consider magnetars, the universe's ultimate electromagnets, born from the wreckage of these mergers. When two neutron stars spiral together, their combined magnetic fields can twist into unfathomable configurations, creating a newborn object with a magnetic field a quadrillion times stronger than Earth's. These forces are so intense they could wipe a credit card clean from halfway to the moon, and they power relentless X-ray screams as the magnetar's crust cracks under magnetic stress. The collision that made your gold jewelry might have also birthed one of these invisible monsters, now lurking silently in some distant corner of the galaxy. Then there are the gamma-ray bursts, the universe's brightest explosions. Neutron star mergers channel their energy into pencil-thin jets, traveling at 99.9% light speed. When these beams slice across our line of sight, we witness short gamma-ray bursts, flashes so powerful they outshine entire galaxies for a few seconds. The afterglow paints an even wilder picture. Photons ricocheting off relativistic particles create polarization patterns that reveal the jet's internal structure, like cosmic X-rays exposing the explosion's bones. Some bursts even come with extended emission, in mysterious X-ray echoes suggesting the merged object might briefly resist collapsing into a black hole, fighting gravity with spin and magnetic fury. The debris fields themselves hide bizarre physics. As ejected material expands, it forms exotic nickel-rich bubbles where atomic nuclei arrange into crystalline patterns unseen on Earth, structures so dense a sugar cube-sized chunk would outweigh Mount Everest. Radioactive decay within this shrapnel powers the kilonova's glow, but the real surprise lies in the lanthanides, rare Earth elements that absorb light so efficiently they render parts of the explosion invisible to conventional telescopes. Only infrared instruments can pierce this cosmic smokescreen, revealing how neutron star collisions manufacture elements we scarcely understand, like promethium, a radioactive oddity with no stable isotopes that somehow survives long enough to influence the explosion's color evolution. Perhaps the strangest byproduct is something we've never directly observed: quark nuggets. Under merger conditions so extreme that neutrons themselves shatter, theorists predict the formation of strange matter, a primordial goo of free quarks that might convert ordinary matter on contact. While definitive proof remains elusive, some astronomers speculate that certain unusual supernovae could be quark stars announcing their birth, ultra-dense objects even more exotic than neutron stars. If these exist, they'd rewrite our understanding of nuclear physics, proving that neutron star collisions don't just rearrange atoms, they dismantle and rebuild matter at its most fundamental level. These phenomena do more than dazzle, they reshape galaxies. Magnetars inject energy into surrounding nebulae, while gamma-ray bursts potentially sterilize planets light years away. The heaviest elements sink into star-forming regions, altering the chemistry of future worlds. Even the gravitational waves from these events carry hidden messages. Subtle distortions in the signal might reveal whether the merged object developed mountains mere millimeters high, enough to warp spacetime detectably as it spins. Every collision is a universe-altering event, scattering not just atoms but new physical laws across the cosmos. The gold is merely the glitter on a far richer tapestry of cosmic transformation, one we're only beginning to decipher. The frontier of neutron star collision research isn't just about confirming what we know, it's about exposing gaps in our understanding that could rewrite physics itself. One tantalizing mystery centers around the mass gap problem, the puzzling absence of stellar remnants between the heaviest known neutron stars and the lightest black holes. When two neutron stars merge, does the resulting object always collapse immediately into a black hole, or could it linger in this theoretical no-man's land as an exotic hybrid object? Upcoming gravitational wave detectors like the Einstein telescope will hunt for vibrations that betray the presence of these strange transitional objects, potentially revealing states of matter so dense they warp the very rules of quantum mechanics. Equally compelling is the hunt for strange star collisions, hypothetical mergers where neutron stars aren't made of neutrons at all, but of free-floating quarks in their most primordial form. These theoretical objects would leave distinct signatures in their gravitational waves, subtle tremors unlike anything we've detected before. A confirmed observation would prove that matter can exist in a state not seen since the first microsecond after the Big Bang, opening an entirely new chapter in nuclear physics. The Kilonova light from such an event might even show unexpected elemental patterns, as quark matter could follow different nuclear reaction pathways when it decompresses. On the cosmic scale, astronomers are racing to understand how neutron star collisions influence galaxy evolution. These events don't just create heavy elements, they inject them into interstellar space at nearly light speed, potentially triggering waves of star formation. New simulations suggest the shockwaves from multiple mergers could carve vast cavities in galactic gas clouds, creating elemental bubbles where next-generation stars form with unusually rich concentrations of gold and platinum. The Vera Rubin Observatory's upcoming sky surveys might catch galaxies in this act of chemical self-enrichment, watching as ancient mergers sculpt the birthplaces of future solar systems. The James Webb Space Telescope offers another revolutionary angle, peering back to the universe's first neutron star collisions. By analyzing the infrared light from galaxies that formed when the cosmos was less than 1 billion years old, astronomers hope to detect the infrared fingerprints of early R-process enrichment. This could reveal whether the very first star's monstrous behemoths, hundreds of times more massive than our Sun, left behind neutron star binaries that merged quickly, or if the universe had to wait for several stellar generations before building its first gold. The answer would rewrite our timeline of cosmic chemical evolution, showing how quickly the universe became capable of forging planets like Earth. Perhaps most mind-bending are the connections to fundamental physics. Neutron star mergers create conditions so extreme they might briefly manifest phenomena predicted by string theory or quantum gravity. Some models suggest the merged core's unimaginable density could warp spacetime into microscopic black holes that evaporate via Hawking radiation, an effect never before observed. Others speculate these collisions might produce action stars, clumps of hypothetical dark matter particles that would decay into detectable gamma-ray flashes. Every new gravitational wave detection brings us closer to spotting these exotic signatures, potentially solving multiple cosmic mysteries in one observation. The next decade promises to transform these questions from speculation into concrete science, with the Laser Interferometer Space Antenna LISA monitoring neutron star binaries years before they collide, and next-generation spectrographs capable of detecting single R-process elements in distant galaxies. We're building the tools to watch cosmic alchemy unfold in real time. Future discoveries might reveal that neutron star collisions aren't just makers of gold, but invisible architects shaping everything from galactic chemistry to the fundamental laws governing reality itself. Each explosion is a Rosetta Stone waiting to be deciphered, holding secrets about how the universe builds its rarest treasures and perhaps why it bothered to make them at all. From the heart of a cataclysmic stellar collision to the palm of your hand, gold's journey spans eons and crosses the unimaginable void of space. Every shimmering ounce represents the ultimate cosmic recycling program, where dying stars beget neutron stars. Their apocalyptic mergers forge precious metals, and the resulting elemental shrapnel eventually finds its way into planets, jewelry, and technology. This isn't just a process, it's a saga written in nuclear fire and gravitational waves, where violence and creation dance together across billions of years. Think about the path just one gold atom has traveled, born in the neutron-rich maelstrom of colliding stellar corpses, flung across light years at relativistic speeds, then frozen inside an asteroid for millennia before raining down on primordial Earth. It might have lain buried in rock for eons until human hands finally extracted and shaped it, transforming stellar ashes into art, currency, or circuitry. The same forces that bent spacetime and lit up galaxies now power your smartphone and gleam on wedding bands, a direct material link between the universe's grandest explosions and our most personal possessions. This cosmic connection runs deeper than mere chemistry. The gold in your devices enables technologies connecting humanity across continents. The uranium from those same stellar explosions heats Earth's core, maintaining the magnetic field that protects all life. Even the iodine in your thyroid, essential for cognition, was forged in these rare Kilonova furnaces. We're not just made of stardust, we're made of the universe's rarest, most violently produced elements, assembled through processes so extreme they still defy full human comprehension. Next time you hold something golden, remember, you're touching the endpoint of a journey that began when two dead stars, each heavier than our sun but smaller than a city, circled each other in a fatal dance. Their collision unleashed energies beyond human analogy, creating conditions unseen since the Big Bang itself. Every civilization that prized gold, from pharaohs to financiers, was unknowingly venerating the aftermath of cosmic detonations older than our planet. Those same explosions still happen today in distant galaxies, scattering future treasure for civilizations yet to arise. So when you look up at the night sky, know this: you're not just an observer of the cosmos, but an active participant in its story. Your very atoms were forged in stellar crucibles, your technology enabled by interstellar alchemy, your existence made possible by ancient explosions that balanced the universe's elemental budget just right. The universe doesn't just exist around us, it exists within us, in the gold of our rings and the uranium in our power plants and the rare earth elements in our devices. The next cosmic gold factory might be detonating right now in some distant galaxy. Its light too faint to see, but its legacy already written in the laws of physics. One day, far in the future, those freshly minted atoms may find their way into new worlds, new technologies, perhaps even new life forms. The cycle that began with neutron stars spinning toward doom continues through us and will outlast us. We're temporary custodians of cosmic treasure, heirs to stellar cataclysms, living proof that the universe can turn destruction into beauty, chaos into connection, and ancient explosions into the foundations of civilization. That's the true magic of gold, not its luster or value, but its story. A story that connects every human who's ever held it to the violent, beautiful processes that shape the cosmos. So keep looking up, keep wondering, and remember, you're not just on Earth. You are Earth, and Earth is the universe, made conscious to admire its own handiwork.